Systems 8, working with scientific notation. I can express estimates of large and small values using scientific notation is our first learning target. And the key word here is scientific notation. You can see it twice. And scientific notation is exactly kind of how it sounds. Scientific, so mostly used with scientists, but mathematicians and engineers use it. And then notation, meaning how to note a number, how to write a number. So I'm going to answer those first two questions right away. Why do we use scientific notation, and what exactly is scientific notation? So I wrote down scientific notation is a way of expressing numbers that are too big or too small to be conveniently written in decimal form. So we'll start with that. Conveniently, meaning easy. We're going to look at numbers that are really, really big and really, really small, and we're going to write a way or note a way that is easier for us to communicate, and it's also easier for us to use in certain arithmetic operations, meaning addition, subtraction, multiplication, and division, and also to compare with. And why do we use it? Well, first of all, it's commonly used by scientists, as I said, mathematicians and engineers, because it is simpler to look at, but we also use it because it's plain and simple easier to read. It's easier to compare with. It's easier to write, and it's easier just to look at and truly understand what kind of number we're looking at. So when I look at scientific notation, I can use that same format, but I know if I'm working with a really small number to a certain decimal place, or if I'm working with a really big number to a certain place value. So it just really simplifies really big and small numbers for scientists, mathematicians, engineers, and I'm sure many other professions out there. So for our first example, we're going to look at here, it's going to be this number. Let's go 2730 000, 000. Okay, so if we're looking at this number, first of all, if we were going to read this number, it's 2,730,000,000. Money I would love to have, but it's quite a big number. And if we're going to use it with our math operations, it might be hard to keep track of the zeros and the place values. So what we're going to do is we're going to change this into scientific notation. So the first step is to take this, excuse me, this large number, and we're going to move that decimal all the way until we get what we call is the mantissa between 1 and 10. So I'll show you what that looks like. So if we, first of all, where's that decimal? Well, any whole number, the decimal's at the end of a whole number because this is the place value of ones, and so that decimal is to the right. And we're just going to move this decimal to the left until I get a new number from either 1 up to 10. So we're going to move this decimal 1, 2, 3, 4, 5, 6, 7, 8, 9. Notice I moved it 9 times. And my new number, because my decimal is what I just moved, is now 2.73. So in scientific notation, this first number, which we call as the mantissa, I'll spell that out for you, mantissa, has to be 1 up to 9.99999. In other words, it can't be 10, so it has to be a single digit. It doesn't matter what's behind the decimal, but it can't be in front of the decimal, can't be anything other than one single digit. So this mantissa in this problem is going to become 2.70. And notice I dropped all these zeros. Okay, we'll count those in. They matter, but when we write this, remember, we're trying to write it more conveniently, more easily. So we're going to drop all those zeros because it's easier to see 2.70. I'm sorry, 2.73. Now, the second part of this is that we take it to a base of 10. So times 10, and when we're doing scientific notation, this is always times 10 to the base of 10, which is what, if you remember from previous years, that's what moves the decimal over to the left or to the right. So when we're multiplying by 10, that is just a place value change each time. And so if we go back to this, remember we counted this out. We counted this out to be 9 because there was 3 here, 3 here, and 3 here where we moved those decimals. We moved it 9 times, so we're going to put it to the exponent of 9. So thinking through this, if we were to work this backwards just to prove it, so if we have 2.73 and we just look at the math of this, it says times 10 9 times. That means times 10 once would move the decimal over to the right once. So now we have 27.3. We move it over again. Now we have 273. So that's the second time. And over again, now we're going to have to add a place value of 0. So that's times 10 3 times, times 10, add a 0, 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 times 10, add a 0. Notice when I do that, I go back to my original large number. So again, this is scientific notation. The first number has to be between 1 and 10. It can be 1, but cannot be 10. And it's always to the base of 10 because that's what moves our decimal over. And then the power of 9 is how many times we move that decimal. Next example. Let's look at a small number. So 0.00000000673. Okay, so we're going to move that decimal just like we had before. We're going to move that decimal. It's right here this time. And we're going to move it till we get, again, one digit. And that one digit has to be between 1 and 10. So we move it once, still don't have a digit between 1 and 10. Twice, 3, 4, 5, 6, 7, 8. Notice I stopped here because now I have a 6 in front of my decimal. So I'm going to write down this mantissa, 6.73, 6 and 73 hundredths. Notice again, I ignored all the or I should say the zeros, the ones that are not important to our place value. And I'm just going to write down the mantissa at 6.73. Remember, it has to be times 10. So it's always times 10 to base because that's what moved our decimal over. Again, I counted 8 times. 1, 2, 3, 4, 5, 6, 7, 8 times. Now, it's not to the power of just 8. I'll put an 8 up here. But if we're going to move it to the left, this is important to start learning. If we move it to the, to the right, we are going to have to take it to the negative eighth. And remembering from last power standard, that when we take something times 10 to the negative first, that is really like 1/10. And so if we were working this backwards, like I did before, and we had the 6.73, and I multiplied it times 10 to the negative 8, so times 10 to the negative first 8 times, I'm going to multiply it by 1/10. Well, that's kind of like dividing by 10. And we learned that if we move it to the left, we're actually dividing in a pattern. So this would be dividing by 10 or multiplying by a tenth. So that's why we would be moving to the left by multiplying by a tenth. So 1, that would be 2, 3, 4, 5, 6, 7, 8. And notice when I do that, when I multiply by 1/10 8 times, or I divide by 10, then I'll move that decimal back to what it looked like in the original problem. So again, notice the pattern here. When you when you have a larger number, the exponent's going to be 9, or in other words, when you move the decimal to the left and begin with, the exponent's going to be positive, and when you move it to the right, the exponent's going to be negative. Okay, let's look at one more example here. Let's go with another, it doesn't matter. Let's go with a bigger number. So 5 4, 3, 2, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay, so if we were dealing with this, let's say it has something to do with planets and how far in inches a certain planet is away from another planet. I mean, this is a very large number. And to work with this, it would be really obnoxiously hard to, first of all, mathematically say. And then if we had to actually do an operation, it would be a big operation to work with. So first step, move the decimal. So where's the decimal? At the end. And we're going to move it until we have it with a 1 to 10 number in front. So I'm going to kind of go by threes here. There's 3, 6, 9, 12, 15, 16. And you can count by ones. It's fine, but I was just going to count by 3 because it's nicely spaced out here. So again, 3, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. It took me 16 place values to get the decimal to have a number of just one single digit between 1 and 10. So we're going to start with 5.1321. And again, I'm going to drop these zeros because they're going to make my number more complex and they're not needed because I'm going to use those place values with my base of 10. Always to a base of 10. And then I'm going to think about how many times did I move it? 16 times. So that's my final answer. In our last example number 4, we're going to work with a really small number. So let's go 0.000000001, 2, and 3. So again, we're going to start where our decimal is. We're going to move the decimal over until we have one digit in front of it that is a non-zero. So there's 2, 3, 4, 5, 6, 7, 8, 9, and 10. So we're going to write down our new number. So our decimal's right here. So that's 1.23 times, remember it's always the base of 10. And since it's a small number, or because I moved the decimal to the right, I'm going to put it to the negative 10th power. So I'm just going to count one more time, make sure I did it right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to the 10th power. And that is how you write very large numbers or very small numbers in scientific notation.